This is June 1st, and at Oklahoma Christian University, this is Engineering 5213, Tools of Operations Research, lecture number 5. This will be recorded only. So tonight, we're going to finish talking about linear optimization problems. Last lecture, we began talking about allocation models, covering models, and ended talking about blended constraints and blending models, all of which were linear optimization models. Linear optimization models are special in that the objective function, which you are trying to either maximize or minimize, is a linear function of the decision variables, the things that we can change or decide on, the things we want the model to choose optimal values for. Also, all of our constraints, which limit which decisions can be made, which limit the values we can assign to those decision variables. They are also linear functions of the decision variables themselves. Tonight, what we're going to talk about is another special class or two of linear optimization models. First, we'll be talking about network models, and then we'll be finishing with integer and binary models. Again, these are all linear optimization functions or linear optimization models, meaning that the functions are still linear in terms of the decision variables, both the objective function and any constraints. So let's just jump straight in. We'll do plenty of examples and then conclude. So network optimization is a special type of linear optimization models that we're going to consider. And really what they do is they describe a system of flows. That is, you have, let's say, some product that you're going to ship from some source to some destination. Or let's say in some other kind of mechanical process, you have something that's moving or flowing from one place to another. And we can represent those kinds of systems as long as they are linear in a linear network optimization. And so we're going to consider several examples that look like that. The difference between network optimization and regular linear optimization that we've talked about so far is the way we're going to represent the problem, and we'll see that in a minute with some diagrams basically made up of circles or bubbles or nodes and edges or arcs between those. So we will represent the source as a particular circle. If we have multiple sources, there will be multiple circles. And then we'll draw arrows from those to destination nodes or destination circles. And those represent the flow of something from its source to its destination. And we will constrain how much we need to flow, how much can flow from any particular source or to any particular destination, as well as maybe the cost or the profit or the goodness of a particular edge between one particular pair of nodes that we may want to optimize using. So let's consider first one very common class of network optimization problems known as transportation problems. So this is where literally we're trying to decide shipping transportation routes from some source locations to some destination locations. So generally what we're trying to do in this kind of a problem is choose how much product or how many of our goods should come from each source and should flow to each destination along particular shipping or transportation routes between each source and destination. Each source destination route has its own cost. That is, maybe its distance between the source and destination. In terms of a higher distance will incur more cost to ship the product, to drive the truck, to use the railway system or any other kind of system to transport from that source to that destination. So obviously in this kind of a problem, what we would like to do is minimize the cost. That is, we'd like to find a way to cheaply ship all of our required product from the sources to their destinations, choosing those routes which will minimize our cost. So here's a quick example we can talk about. An electronics company is planning next week's shipments from its 3 manufacturing plants to its 4 distribution warehouses, and it's seeking a minimum cost shipping schedule. So we have 3 source plants where goods are being made and 4 destination warehouses where we need the goods shipped after they've been made. Each plant has a potential capacity. That is, each plant has a maximum amount that it can produce, expressed in terms of number of cartons of product. And each warehouse has a requirement. That is, it needs a minimum amount of product in order to meet, say, the demands of the sales network or the sales location nearby. So there are 12 possible shipping routes, and for each route, the unit shipping cost is known. That is, from each of our 3 plants, we could ship some product to each of the 4 warehouses, but each of those routes, 3 plants, 4 warehouses, 12 total routes, each of them has its own cost associated with it in terms of a cost per carton of product. So whatever our cartons are, or units of product, we have the capacities of the plants. We need to ship that capacity, those amounts, to each of the warehouses according to their demand or their requirement. So some may need more than others. And we want to choose the routes between sources and destinations that will add up to the lowest possible cost. So here is a table of the requirements for this problem, or the constraints as we will derive them, listed as our 3 plants on the left: Minneapolis, Pittsburgh, and Tucson. So 3 locations that our manufacturing plants exist. And in the columns there, we see our 4 warehouse locations: Atlanta, Boston, Chicago, and Denver. Now each plant, the 3 plants, have a capacity listed on the far right there. So Minneapolis can produce 9,000 units, which is less than Pittsburgh and Tucson, which can produce 12,000 and 13,000 respectively. But in addition to the plant capacities, so our sources have a capacity, but our destinations, our warehouses, they have a requirement or a demand. That is how many cartons they need shipped to them from any one or multiple of the plants. And then for each plant warehouse pairing, we have a unit cost in terms of here dollars and cents of how much it would cost to ship a single unit or carton of our product. So we're going to have to ship something like 7,500 cartons to the Atlanta warehouse. Those could be made up of cartons coming from Minneapolis and or Pittsburgh and or Tucson. Now obviously it looks like from this chart that Pittsburgh is the cheapest place to ship product to Atlanta. It's closer, presumably, and it's far cheaper. It's 36 cents. So if we could, we'd like the 7,500 units that Atlanta needs to come possibly from Pittsburgh, because Pittsburgh would have enough capacity and it would be cheaper. However, that might be in conflict with other parameters of the model. So we may also find, say, that Pittsburgh is the cheapest place to ship to Boston, and it is. And so Pittsburgh cannot possibly ship its 12,000 units of product to both Atlanta and Boston to meet both of their demands, both of their requirements. So we're going to have to find a way to balance where product can come from, the plants and their capacities, and where the product needs to go to, the warehouses and their requirements, subject to minimizing costs. Now I talked about how we would represent network optimization problems using diagrams of circles and arcs or edges. I'd like to represent that now on the whiteboard. So in our example, we had 3 sources, so I'll represent those with 3 simple circles. We had a Minneapolis, a Pittsburgh, and a Tucson warehouse, plant, manufacturing plant. And we needed to ship product from each of those 3 to 4 different warehouses that need the product. So we had one in Atlanta, we had one in Boston, we had one in Chicago, and one in Denver. Okay? And we know, for example, that Minneapolis could ship to any one of these, so we'll represent that with 4 different arcs, but the cost of shipping each unit or each carton of our product from Minneapolis to each of the 4 warehouses is different. So the cost associated with that shipping route is different for each one. So for example, to ship from Minneapolis to Atlanta costs 60 cents per carton. the cost for shipping from Minneapolis to Boston is 56 cents per carton. Okay, and so forth. So we can fill in each of those numbers. Now, we could also ship from Pittsburgh to each of the 4 warehouses. So that another 4 edges. And similarly, we could do the same for Tucson. Okay? Now, what we want to find is what would be the minimum amount. That is, likely we don't want to ship some product on all 12 of these shipping routes. We'd likely try to find ways that a particular warehouse could get all the product it requires from a single cheap manufacturing plant. That is, whatever plant can ship the cheapest to that warehouse would likely want to do all of that. So what we expect to see, although there's 12 options for lines or edges in this chart, what we'd like to see probably is very few. As few as hopefully 4 lines. That is, each warehouse would get all the product it requires from a single plant, which is the cheapest. Now, in addition to these 12 arcs or lines that we could draw here, I also want to show how we would represent both the requirement, that is, how much product we need coming into each warehouse total, and that is the demands or the requirements for those. So Atlanta needs 7,500 product to be shipped to it from any one or multiple of the 3 plants. For example, Boston needs 8,500. Chicago needs 9,500. And finally, Denver needs 8,000. Those are going to be 4 of the constraints that will make up our linear network optimization problem. That is, we want whatever comes from Minneapolis to Atlanta, plus whatever comes from Pittsburgh to Atlanta, plus whatever comes from Tucson to Atlanta, to add up to 7,500. Now, there's also limits on how much each manufacturing plant can send out. That is, it has a capacity of what it can provide. And those are provided as well as 9,000, 12,000, and 13,000. So we'll represent those as a single edge or a single link pointing into the manufacturing plants that say this is how much they have that can be sent out. For each destination, that is each warehouse, we represent on the backside of those a single arrow which represents how much needs to have come in that they have to meet for their requirement. So the idea is we need to find the optimal solution in terms of what goes in the middle of this network diagram that minimizes costs associated with the shipments. Okay? So let's switch now to looking at Excel, and we'll find how we can set up this kind of a problem. Okay? So we know we have the 3 plants. We have a plant in Minneapolis, we have a plant in Pittsburgh, we have a plant in Tucson. Okay? And we know we have 4 different destinations, 4 different warehouses. Okay? So we have 4 different warehouses represented as Atlanta, Boston, Chicago, and Denver. Okay? Now at the intersection of each of these plants, here I've represented in rows, and each of these warehouses represented in columns, I'm going to put the unit cost for shipments that go to those places. So to get to Atlanta requires either 60, 36, or 65 cents each, whether or not they're coming from the plants in Minneapolis, Pittsburgh, or Tucson, and so forth. So I'll fill in the rest of these. Now, because these are dollar amounts, let's go ahead and format them to look so. Okay. Now, for each plant represented in a row, there is a capacity that that plant can provide. So 9,000, 12,000, and 13,000. Now those aren't dollar amounts, those are number of cartons, number of product units that can be shipped out of each plant. But also there are requirements or demands to be filled at each warehouse. So Atlanta requires 7,500, Boston requires 8,500, Chicago requires 9,500, and Denver requires 8,000. Okay? And again, those aren't necessarily dollar amounts, those are numbers of units of our product that need to be shipped there. Okay? So we have basically the problem set up in a way that we can represent it here as a very simple table. Okay? So I'm going to put a box around these to show and distinguish them as being unit costs as opposed to capacities and requirements. Okay? So what we want to do is we want to find how can we choose which routes to use. That is, we know the cost of the routes, we know how much has to be shipped total to each of the destinations from each of the warehouse or each of the plants or the sources. So here we're going to define and set as our variables, as our decision variables, how much product needs to occur or how much product needs to flow on each of those 12 possible shipping routes. Okay. Now here I'm going to fill it in with zeros everywhere because we don't know the answer yet. We might imagine that there's ways we can guess and find out ways to add up all that gets shipped to Atlanta here in column C, rows 9 through 11. We want that to add up to what Atlanta needs, which is 7,500. So here I'm going to calculate how much gets shipped to Atlanta as the sum of those three and copy that formula over for each of the other warehouses. And so forth for each plant that needs to ship, so each row represented by a plant, how much gets shipped out of that is going to have to be limited by the capacity of that plant. So here I've added all that up. And then finally, what we're going to compute as our objective, which will be total cost, is going to be, well, if you'll remember back, our linear optimization programs tend to use the sum product, which usually we've used as a multiplying one row of cells by another row of cells. But in this case, we're going to multiply this whole grid of 12 unit costs for each route, multiply that by this whole grid here of how many units will be shipped on that particular route. So we can use sum product to multiply whole tables, and it will just multiply each individual pair of cells and then add up the results. Okay? And that will be our objective that we will try to minimize. Okay? So we have our decision variables. We have computed how much product gets shipped from each plant and to each warehouse, which we will have constrained by, well, we have to ship to each warehouse at least as much as they need. That is, at minimum, this much. And we can only ship from the plants as much as their capacity. So anything less than or equal to their capacities. And then we have our objective. So let's just go ahead and add that in. So I'm going to highlight all the decision variables, all the amounts that we can choose, which are the amounts of product to be shipped on each route. We'll make those our decision variables. And then we basically have two kinds of constraints. That is, we want to limit the amount shipped to each plant. We're going to constrain that to be, well, we can't ship any more than the capacity. So that must be less than or equal to the capacity. And then our other kind of constraint, we're going to constrain all four sums that represent how much is shipped to each warehouse. That must be constrained to be at least as or greater than or equal to the requirement for those warehouses. So these four cells here. So although we have 7 total constraints, there's a collection of 3 constraints that look very similar and 4 constraints that look very similar. And then of course our objective, we need to mark that as something we're wanting to minimize in this case. So obviously the values I put in here at 0, although they achieve a very low cost, do not meet the objectives in that this value here is not at least as big as 7,500 as it should be. So now that we've put in the parameters for our model, we can go ahead and run the linear optimization. Oh, have a problem here. So let's make sure we've specified correctly B15 as the objective. So we're minimizing the sum product of all the unit costs by the number of units shipped. Our decision variables are all C9 through F11, the amounts that can be shipped each where. So for example, if we wanted to take advantage of the cheap route of shipping from Pittsburgh to Atlanta, there we go. So we could do that, and so forth. All right, so let's look at our constraint. C12 through F12, that is, the amounts shipped to each warehouse must be greater than or equal to the requirements of each. Okay, let's make sure I typed in the right values there. And then G9 through G11, those values shipped from each plant, summed up here, must be less than or equal to, that is, they can't be any greater than G3 through G5, the capacities. And again, check that I have those units correct. Okay. And then our total cost, which really should be formatted to look as a number, would be there. Select the right engine algorithm to run. In this case, we want the linear programming or the linear optimization algorithm. Make sure I have no other parameters selected anywhere. There we go. Further. So here's the problem, obviously, is that it's determining that it can select negative values, which means it's hard to find a correct or an optimal solution when it's allowed to ship negative product to offset, and instead of incurring a cost, we get some amount back. So obviously there's one more constraint, the typical one that we don't usually specify in a problem statement, but always have to be wary of, which is, do the decision variables have to be constrained to be at least 0? And again, the easiest way to represent that is on the solver options and model specifications engine tab. We can tell the engine that it can assume or should assume that decisions that the variables it sets must be non-negative. So now let's do that. There we go. So what it's determined is that the product that goes to Atlanta should come from actually two locations, Pittsburgh and Tucson. The product that should be shipped to Boston, all 8,500 it needs, should come from Pittsburgh, which is the cheapest route to get to Boston. Denver, all of its product comes from Tucson, which isn't quite the cheapest route to get to Denver, but it's not far off, it's close. And obviously, Denver can't get its product from Minneapolis, though it is cheaper, simply because Minneapolis is shipping so much of its product to Chicago, which is the cheapest route to get to Chicago by far. Okay, even better than Tucson or Pittsburgh by quite a bit. So, but Chicago can't get all 9,500 from Minneapolis because Minneapolis only has a capacity of 9,000. So all of Minneapolis's product goes to Chicago, but Chicago still has to get 500 units more from somewhere. And in this case, although it might be, it's definitely cheaper to get it from Pittsburgh, only getting 500 units, it's cheaper to get those from Tucson, though that's more expensive, so that Tucson can send its product both to Boston, all of its product, or all the product needed at Boston, comes from Pittsburgh and the rest of it to Atlanta, for a minimum total cost of $12,025. Okay, so quickly, just to review, we've set up the problem as a grid, okay, where we've put the unit costs, we've put the source location capacities, that how much they can send maximum, and the destination location requirements or demand, that is how much they need at least. And then we've represented the decisions that can be made as another grid where we've summed each row and each column so that we can constrain all the column sums to be greater than or equal to the demands, and all the row sums to be less than or equal to the capacities. And then our objective is computed simply as the sum product of all the unit costs by how much is shipped on that particular route. So each of these zeros contributes nothing to the total cost, whereas each of these non-zero values gets multiplied by their corresponding unit cost, and then that is summed up. Okay? Now, we'll come back in a few minutes and revisit this problem, but before we do that, let's talk about another kind of network optimization problem. That is a network optimization problem. So transportation was the first example where we're shipping. Another common class of network optimization problems is one called assignment, where it's basically a specialized case of transportation where all the demands, all the requirements are one, as well as all the capacities. So for example, let's say as a swimming coach, you need to assign each of your 4 swimmers to swim a different stroke, a different way of swimming in a relay. So obviously you have 4 swimmers. There are 4 different strokes in the relay, 4 different spots in the relay team, and everyone must be assigned to only one spot, and every spot must have only one assigned swimmer. So we have essentially 4 sources, swimmers, and 4 destinations or strokes that we want to assign them to. And we can only assign one person to one place, and every place can only be assigned one person. And we're going to do this in order to minimize the relay swim team time. So we know how long each swimmer takes to swim each stroke, and we want to assign the swimmers to the stroke they can swim, hopefully the fastest, faster than anyone else, in order to minimize the total time it would take the entire relay team to swim. So for example, here's a table of some example 4 swimmers and 4 strokes, and how long each swimmer takes to swim each stroke. So again, we're going to take this problem and represent it in Excel, although we can represent that as well in a diagram. So let's go to Excel, and we have our 4 swimmers. So in this case, I believe our swimmers' names were something like Todd, Betsy, Lee, and Carly. And we had 4 strokes that we need to assign them to. So the butterfly, the breaststroke, the backstroke, and the freestyle. And then for each combination of a swimmer and stroke, we know, based on maybe measurements, how long on average that swimmer takes to swim that stroke. So we can input those values. Okay. Again, I'm just going to put a border around these to represent them. And then we have our decision variables that we're going to set up for the problem. So we know each swimmer here, and we know each stroke that they can swim. And basically we want to find an assignment, that is, values to put in here that add each column up and each row up adds to be 1. So a specialized form of sort of transportation in that every route can only be assigned from one source and to one destination. That is, each swimmer can only swim one stroke. Each stroke can only be swam by one swimmer. So we could sum up each column and sum up each row. Okay. We could represent capacities and demands up here, but since we know this is an assignment kind of problem where we're assigning swimmers to strokes, the capacities are all 1, the demands are all 1, so we don't necessarily need to represent those. But we do need to know the objective, which is the total swim time for the relay team, which again is just computed by multiplying each swimmer's assigned stroke by how long it takes that swimmer to swim that stroke. Okay, so that's a total amount of time that we think the relay team will take, because again, only each swimmer can only swim one stroke, and each stroke will only be swam by one swimmer. So we're guaranteed to only multiply 4 different values and add them up. Okay, and what we multiply them by will always be 1, because we're constrained to only have 1s and 0s, because we only need a 1 in each row and a 1 in each column. Okay, so we'll create the model by declaring these as our decision variables. This is the objective we want to minimize, and each row is going to be constrained to be equal to 1. Okay, this is an assignment problem, so the constraints here we can represent as being purely equal to 1. Okay, execute that model. Oh, unbounded, because again we need to constrain and let the solver know that each assignment cannot be unassigned. That is, we can't assign somebody to negative amounts of a stroke to swim. Okay, so it looks like here they found that the optimal assignment is to have Todd swim the backstroke, Betsy swim the freestyle, Lee swim the breaststroke, and Carly swim the butterfly. Okay, for a total swim time of 173. Now, Todd was not the fastest person to swim the backstroke, but if you look, Todd is not the fastest swimmer to swim any particular stroke. So we had to find what stroke to assign him, even though he wouldn't be the fastest at it, in order to minimize the amount of time everyone else could swim their strokes. So we did assign Carly the butterfly, at which she is the fastest. We did assign Lee the breaststroke, at which Lee is the fastest. And we did assign Betsy the freestyle, at which she is the fastest swimmer, which left the backstroke available for Todd, and a best objective. Okay. Now, actually, before we move on and talk about additional network optimization problems, I want to go back and sort of review what we did in the transportation model here. So we found a way to ship product from each plant to each warehouse to minimize total cost. But we might ask questions like, using sensitivity, optimization sensitivity, how much different one particular cost might have to be before we would change the optimal solution. Okay, and so to do that, we'll take a short break and then come back and visit that problem again using optimization sensitivity.